Hi friends, welcome back on our YouTube channel. Today I am here with another lecture of statistical mechanics in which we will discuss derivation of thermodynamics. So let's start derivation of thermodynamics. Here we will discuss about derivation of thermodynamics and also about how can we find all the thermodynamic function of a system. So these two topics we will discuss in our current lecture. So first of all, derivation of thermodynamics. For deriving thermodynamics, we consider that the system is under quasi-static thermodynamic transformation. It means this system neither in static thermodynamic transformation nor it is in chaotic thermodynamic transformation. It is under quasi-static thermodynamic transformation. A quasi-thermodynamic transformation corresponds to a slow variation of energy and volume induced by coupling the system to external agents. The variation is so slow that at every instant we have a microcanonical ensemble. Now, what are the types of ensemble? We have already discussed in our earlier lecture and the link of that lecture is given in description box. So, here the variation is so slow that at every instant we have a microcanonical ensemble. Since entropy S is a function of energy and volume, so the change in entropy in an infinitesimal small transformation is given by ds is equal to del S upon del E at V dE plus del S by del V at E dV. So, by differentiating this equation, we get ds here. Now, del S by del E at V equal to 1 upon T. So, this is 1 upon T. And also, del S by del V at E equal to P by T. So, we replace this by 1 upon T and this bracket by P upon T. So, ds is equal to dE by T plus P by T dV. Now, on taking common 1 upon T from here, ds is equal to 1 upon T and in bracket dE plus P dV. And if we transfer this T from here to here, then TdS is equal to dE plus PdV. Now, we transfer PdV from here to here, so dE equal to TdS minus PdV. And this is first law of thermodynamics. In this way, we can obtain first law of thermodynamics, which is actually conservation of energy, according to which energy can neither be created nor be destroyed. It can only be transformed from one form to another form. Thus, by using classical statistical mechanics, we can find first and second law of thermodynamics, that is dE equal to TdS minus PdV, which is our first law of thermodynamics, and dE equal to TdS, which is our second law of thermodynamics. So, by using classical statistical mechanics, we can derive first and second law of thermodynamics. And also all thermodynamic function in terms of molecular interaction. Third law of thermodynamics can be obtained by quantum mechanical statistics, not by using classical statistical mechanics. So, by using classical statistical mechanics, we can obtain first and second law of thermodynamics, whereas by using quantum statistical mechanics, we can derive third law of thermodynamics. Now, how can we find all the thermodynamic function of a system? For it, we consider an isolated system having volume V and energy E within a small uncertainty del E is very much less than E. Now, calculate the density of state omega of the system by using omega equal to del by del E of sigma E. So, by using this relation, we can calculate the density of state of the system omega E. Now, we find the entropy by using S is equal to K log gamma E, S equal to K log omega E, or by using S equal to K log sigma E. So, here we obtain the value of omega E, and by using any one relation from here, we obtain the value of entropy. Now, find E from above equation in terms of entropy and volume. The resulting function is the thermodynamic internal energy of the system, that is U. So, U is equal to E. From internal energy U, other thermodynamic function can be derived as T equal to del U by del S at V. This is absolute temperature, and pressure by using P equal to minus del U by del V at constant entropy, and Helmholtz free energy A equal to U minus Ts, and Gibbs potential or Gibbs free energy G equal to U plus PV minus Ts, and also heat capacity at constant volume, that is Cv equal to del U by del T at V. So, if we know the value of internal energy U, then we can find all the thermodynamic function by using these relations. Here we end our session. In today's session of statistical mechanics, we have discussed about derivation of thermodynamics. So, goodbye.